All right, good morning. So exactly, we want to talk about the particularly the X-ray TDE, which we've found in the Slew survey. So thanks to Stephanie for generally introducing X-ray tidal disruption events. So this is our Slew survey. This is our basically our mechanism for detecting tidal disruption events. And what, as you can imagine, what it does is the XMM looks from one observation to another observation, keeps the cameras open, and it gets something like 10 seconds of exposure time on each particular piece of sky, which is not great, but the cameras are quite large, and so roughly it gives you the same sort of sensitivity as the ROSAT or Sky survey. And this allows you to actually do a comparison between what we see and what ROSAT saw 20 years ago, and then pick out basically anything which is brighter, any transients. There's a few flare stars, a few active AGN, but we also see tidal disruption events. And what we particularly see, because the sensitivity is not great, is we're seeing tidal disruption events which are from bright in the X-rays and from relatively nearby galaxies, in fact. Okay, so I think, as people have mentioned, there's been a bit of an explosion in the literature over the last 18 months or so. And to me, these are the four questions which have come out from that, from these papers. Is that A, why is it that, given the models, that circularization should perhaps be a bit further out than previously expected? We always see prompt, quickly rising, short plateau, quickly decaying tidal disruption events. Why do most of the tidal disruption events we see in the X-rays have soft emission and not have power laws like the AGN do? The outflows that we see, particularly from 14 Li, somebody mentioned in one of the papers that these are ubiquitous, or can we say if they're ubiquitous or not given the data? And then looking at the fact that the low temperature optical events is the fact that could this be from reprocessing or not? Can we say anything from the data we've got? Okay, so the fast rise events, I mean, it's absolutely true that whether you look in the X-rays or the UV or the optical, we always see a rise which takes place over weeks, maybe a month at the latest. And then a plateau which is kind of like negligible, and then it starts to decay almost immediately. So why is this? Okay, in this particular year, then there's been several papers on this, and I think at least these three papers have been talking about having circularization quite close in, quite far out rather, in which case then you should be getting some sort of relatively slow infall of the material. The accretion disk extends, and so you get a relatively slow rise to peak. The material is extended, so you get more material accreting more slowly, so you should have more of a plateau before it then joins off on the T to the minus 5 over 3 as before. Thanks for the plot. So fine, and I particularly like this phrase in James and Enrico's paper saying that probably we don't see this because it's a selection effect. And in an optical, maybe it is, because in the optical then you're certainly seeing you're looking for very sharp rises in the flux. But in the X-rays, we've got this 20-year baseline between what ROSAT sees and what we see, in which case there's absolutely no bias at all now. So we should be seeing what is really out there. So okay, this is the first ever source that we saw, and I think it still holds the record for the closest source at about 20 megaparsecs. It's a typical tidal disruption event as far as the X-rays are concerned anyway. Falls off quite nicely as T to the minus 5 over 3. It's got a temperature of 80 eV or so if you fit it as a single black body. And when you look at the optical spectrum, then there are sort of emission lines, but at a very, very low level, so that you can constrain any sort of persistent AGN to below 10 to the 40, let's say. So which is a couple of orders of magnitude below the peak luminosity that we see. Now, that's fine and everything's consistent, except for there's some change to the processing software which allowed us to look at some very early slews. And then one of these slews showed that there's actually the peak flux was already there 18 months beforehand, in which case, because you've got this quite nice t to the minus 5 over 3, then it's very difficult to then put it here. You go up too fast, basically. So there's no way that this is on a part of a standard curve, and then this then looks like you're on a rather flat plateau type area for 18 months or so, which looks much more like the sort of light curves that these late circularizations are predicting. However, we discovered this before all those papers came out, and so when I saw this I started reinterpreting it as an AGN event, in fact. So with AGNs, I mean, all this soft emission comes from right close in, okay? And like with galactic binaries, then there's the idea that for some reason then you get a hole in the middle, you haven't got any soft emission, it falls in, material falls in, you get a change in state, you've got lots of soft emission, and you get this soft flare. It goes into the soft state, let's say. But for AGN, you just don't have the time to do that. It takes like decades to do that, and to get a factor 100 rise. So what people propose in binaries as well, because they have a similar sort of problem, is that you get the viscous infall slowly, but then you have to have some sort of instability. So the material gets so compressed that the radiation pressure takes over. You get a thermal runaway of a heating wave, the material expands, you get a thicker disk, and then you can get this very large factor 100 rise in the soft flux. This material then gets relatively quickly eaten, and then it goes back to the low soft state, let's say, or back to the low hard state, in fact. So fine, I mean, just at this time the IC359, which Stephanie talked about in detail, came along, in fact. And so then we applied this model to this second curve from IC3599, where it seems to work okay, and the timescales are so fast, in fact, that if it is an AGN, then it's got to be some mechanism like that. Now, but putting it back to NGC 3599, then because this is such a weak persistent AGN, and because we've only seen one flare from it, then I think I still prefer the explanation that this is more like a delayed TDE, or possibly because the luminosity is quite low, then it could be stripping of the atmosphere of a red giant, in fact, because we're only at 10 to the 42. So, which gives you this kind of like slower rise and long plateau. Okay, so the second question is, why isn't there power law emission? So we all know in AGN that in like 99.99% of AGN, then not only do they have some sort of thermal disk, but they also have a power law, which is supposedly thought to be by hot electrons which are Compton upscattering, let's say, the photons. So that's fine, but in almost all of the tidal disruptions we see, then the X-rays are soft with no hint of a power law. This is the example from Linatel, where we see it's actually got 170 eV. It's quite a small black hole, but no power law. And I think this is the same for almost all of the sources that Peter Maxim has found as well, and the early ROSAT events, and most of our events. Whereas I think when you look at thousands and thousands of AGN, then there's only like 3 or 4 events which don't have power laws and do have X-rays. Okay, so there are, however, because Roland Walter in particular has been looking at the higher energies surveys, and then starting to find a few power laws coming in. So with the integral and the swift batch sources, and we found one last year which may be a AGN, maybe a tidal disruption event. This is actually the spectrum of it. And I think the Bradchenko sources also, although you didn't have many photons, had a relatively hard slope, let's say of 1.8 or so. Okay, so let me introduce you to the new source that we found recently. This is 2MASS X0740. We saw it with a factor 15 increase in X-ray flux above ROSAT. This here at a redshift of 0.017, and normally it wouldn't have been enough of a flare to actually cause us to monitor it. But in this particular case, then it had a 2MASS spectrum from the 2MASS redshift survey, which showed pretty clearly that it was actually an inactive galaxy. So we decided that we were going to monitor it anyway. Now, when we followed it with Swift, then we saw it dropped off here in the X-rays relatively rapidly at first, at least, by a factor of a few. And also in the UV filters, then we found in the end like a 3 magnitude change in the sort of short wavelength filters, and a 1 magnitude change in the long wavelength, the UW1 filter. So there's obviously something's going on here. It's pretty interesting in an inactive galaxy. And then when we looked at it with a long XMM observation, then we see in this case indeed then it does have the high energy 2 to 10 keV photons with a reasonable slope. So you can roughly fit this at least with a single black body of 8 TeV or so, and a power law of a typical slope around 2. So it's quite nice. We've got lots of flux, so we can investigate this now. So when we look at the actual light curve in the various different bands, and in the 2 to 10 keV band it's falling off it's falling off anyway over 500 days. The soft X-ray flux is doing something similar, although in detail it's a bit different, and the UV filters are falling off a little bit slower. So it's not actually to the -5/3, and in fact we get a slope of about -1 in the X-rays and -0.5 or so in the UV. But nevertheless, I think it's looking like a definite tidal disruption event at this stage anyway. Now this is one of the things where we get the UV filters and we get the soft X-rays, and you can actually connect them very, very nicely. We've got quite good data here. And so using a multicolour disk model, which we tend to use this Optex AGN model which Chris Dunn produced, which has got multicolour thin disk with the Novikov Thorne emissivity profile. And then you can, without any tricks or renormalizing, just with the standard reddening at the optical and the galactic NH, nothing else, then you can get these points to fit immediately. This gives you a very good handle on the black hole mass, if you assume that what the spin is. So with a spin of 0, then we get a reasonably tight constraint of 2 times 10 to the 6 solar masses for the black hole, which from the luminosity is giving us a Edding ratio of about 0.1. This is already a factor 10 down on what we saw at the peak, so that means that at peak at least the Eddington ratio is going to be about 1, so Eddington limited probably. Of course, if you have a higher spin, then this allows you, as we saw in Jane Dye's talk, to go to higher masses. But of course we've got absolutely no constraints on that at the moment. Now another thing is that if you look at this as the short-term light curve, this is views of 10,000 seconds, and we see factor 5 variability in the soft X-rays on these sort of time scales, and a doubling time of something like 400 seconds. So by the standard arguments, then this also tells you that the black hole mass is just a few times 10 to the 6 or so. So this is looking all fairly consistent. You may notice, or you probably can't, that at the higher energies there's a little bit of a problem with the fitting. And so in fact, if we look at it here, then although we can fit it broadly, the X-rays with a multicolour multicolour black body at the low energies and then a power law at the high energies, it doesn't actually fit perfectly, and there's some sort of excess here, let's say. Now it's very tempting to put that excess as reflection. I mean, obviously we've got the power law, we've got lots of material in the middle. You might expect to see some sort of MCG 630 reflection from the middle, either with narrow lines or with broad lines. But we have the same problem as the AGN people, in fact, is that you can fit this equally well by changing the absorption or by putting in emission. So we'll do it the easy way and we'll put in absorption, and so if you fit this with an absorber, then you've got something like 10 to the 23 of material coming off, covering factors of 80% or so, but it has to be reasonably highly ionized because you've got no absorption lines at the soft energies, so you've got absorption of 2 also. Okay, better move on a bit. The second observation is showing you that when he comes down, it's quite interesting really, because the soft X-rays have changed enormously from one observation to the second one, which is 300 days later. But the medium NAJs 1 to 3 keV haven't changed at all, at least in flux. And then this excess seems to have gone away a bit. So it's perfectly reasonable that the emission from the thermal component has died away, which gives you the change here. Exactly what's happening at the high energies, we're not sure. It could be a change in absorption, or maybe the power law slopes change, which would also give you this effect. So the modelling at the moment is ambiguous, and we need to work on it a bit more, I guess. Okay, so we took an optical spectrum 30 days later, which doesn't show any broad lines, and confirms that it's not an AGN of any sort. Right, so ubiquitous absorption. Just like to have a quick look at this, and not got time really to go into it, but I mean, I was extremely sceptical when I saw that. But actually thinking about all the AGNs, all the X-ray TDE that we've seen, we can't say that there's any one which doesn't show absorption. So it's quite possible that there are outflows from all of these sources. And I can't find an example which shows that there isn't in any particular cases. Okay, so finally, looking at this, the idea that the optical emission is caused by outflows which are then reprocessed in this UV X-ray disk emission. I mean, it's a nice idea, and so I thought I'd look at all the sources which we actually got in the literature which have had multi-wavelength coverage, and there's actually not so many of them, probably only about 10 or so. Now the ones which I've got good optical, let's say they've got an optical flare but they don't have an X-ray flare at all, are these two, I believe. So in this particular case, these two do agree, let's say, with that scenario. But then there's these 4 sources where you've got your optical flare, which is certainly at a few times 10 to the 4K, but then you do have an X-ray flare as well. Although at least in one of these cases, then there's the strong absorption, and the others it's just not known because the X-ray spectrum wasn't good enough to say. So whether this now can start putting any sort of constraints on the covering fraction, let's say, of the reprocessor, and whether we've got the absorption which is killing off the X-rays in the line of sight. Probably there's still not enough statistics, but at least in sources like this, then I think we can start to look at those sort of models anyway, to see if that's a plausible scenario or not. I guess I'm out of time now, so okay, thank you very much. Of
the visible mass also.
Yeah. Oh, sugar. Come in. Yeah. Yeah, okay.
Yeah, my question was also about the spectrum. So it seems like there's nothing happening with respect to the host, even though in Swift UVOT you do see.
Yeah, okay, fine. So it's true, but I think that's just an extension of the hot the hot accretion disk. So by the time you get down to the U filter, then the change is only half a magnitude, and in the B filter it's like 0.1 magnitude or something. So I think you're really absolutely not seeing any optical change at all. There's no optical flare basically. Yeah.
Well, that really argues against reprocessing, because that is predicted to go all the way down to the optical, whereas this is
right.
So you're saying you can fit the UV and soft X-ray with the multi-component.
Yeah, yeah, there's no need for any optical. Sure.
So, and the last speaker,